Hello there again. Welcome back. This is just a short, um, hopefully short overview of a concept that I mentioned in the last one, and I figured since the idea is so important and so easy to demonstrate that I thought I'd just do it quickly give you an example of this whole idea of marshalling. If you know what marshalling is, you can go to and hit pause or go home or something. Now here what I've done is I've created a simple project. Now I'd like you to ignore all this other stuff and just look at this code here. Now what you see are some print outlines. I've put DTS 1 and 2. Now first thing I want to mention is that these calls will happen in order. Okay, so this will get printed out, then this, and so on and so forth. And the ones that end with a 2, I think, yes. The ones that end with a 2 are going to occur in a different thread context. That is, there will be another thread alive called the marshalling thread, within which these prints will occur, and by the time we get back to this line, we'll be back in our own thread. And in both cases, it'll be on this line. So let's just see if it's true and if it happens. I should have put a breakpoint there. I will. Next, for the next one, press any key to continue. Now this is a 1BCC, the thread ID which is being printed out with the line get current thread ID. Okay, now I'm printing hello world backwards, and you'll notice that that's not in hex now. Let's see what it says. Now that's a different thread ID. Okay. Okay. F5 again. Now we're back in the same function. I haven't printed it out yet. In this thread again. Okay. So all these various prints are happening in one or another thread. Okay. Now I'm mixing it up. Normally what one wants is for a certain class of calls to occur, as you're calling them in one thread. You want the context to be switched to another thread. That is a different stack, a different thread, almost like a different process. Now, that process is called marshalling. Now, I can easily do this with any function, and I'm going to make a macro, to do this. And I'll show you how I've implemented this. Now, we'll assume this is the marshalling thread. Okay, that is, we want all of our. Suppose we want all of our prints to not happen in our thread where we call them, although we want to block until the operation is complete, but we want it to occur in a different context, a different thread. Okay? And that's what these two ones do. They end up calling put S1, but in a different thread. And then it goes to the next line. How is that possible? Well, first we create the thread. This is documented. As I said, Windows messages, which is what I'm going to be using here, like get message, don't require a window. You can post messages to a thread. However, by default, a thread, when it's created, doesn't have a message queue. And one of the suggested workarounds for that is to keep posting thread messages to the thread until you get one that succeeds. Then it will have a message queue, and then it's ready to receive messages. Now, this is the thread proc. Okay, and I'll get back to the thread proc in a minute. Here's the implementation of put S2. First, we start with an interface called a marshal or marshaller, which contains a signal object, okay, which starts out unset. Okay, a new object. These new manual reset objects start out in the, well, it says null, true, false, null. No, true, false, no, false. Okay, so initial state is false. False means unset. So this is not set initially. A pure virtual function has to be implemented by anyone who derives from this, called invoke. Now that's to invoke whatever the marshal procedure is that we want to occur in our thread. Wait here is a function which waits for this thing, which was initially unsignaled, to become signaled. Okay, that's what this comparison says. So now I could make a macro out of this. I can just put a number, append function name, append argument struct, append return value. This is the implementation for put s. Its arguments are a string, its arguments are a string, and its return value is an int. Now, I'm using ts string because all of this is happening within our process, and it turns out that our ts string thing is relatively thread safe. It doesn't use any globals. It uses malloc, which is thread safe. Things on the stack are okay. So it's okay to use our regular string. The constructor takes the argument value, sets the return value to some garbage, and when invoke is called, I set the return value to that function for S1 of message. Okay? Now how does it get invoked? Here is, in this particular case for put s, I create a pointer to a put s function called marshaled put s, and then I post a thread message to my thread that I've created with a special invoke call message I decided on WMF plus 1, and a pointer to the I-marshaled interface. Then I wait for that process to complete. Now I set the return value to the object's return value. Okay, all of these things, we can put this in a template. Return value could be complex type. And then I return the return value from this. So I don't really need to put S1. It's good enough I could have printed it out here. Or in that invoke. This I could have done that. Put S. Delete the object, the function call object, and return the value. Now, in the thread proc, it's important to get this correct. We don't want it to go on forever. Okay. Now, I've passed in a pointer to another signal object, a waitable object, which tells us when to quit. Okay. So this could really say you could say while quit signal is not set. However, you can get stuck if you do it that way. It's better to use this wait for multiple objects, message wait for multiple objects, which means that I can get out of this wait state in two cases. One, the signal, or it can take an array of signals. One of them gets signaled, or there's something in my message queue. Now, if the reason for the wait to have completed is wait object 0, okay, then that would mean that this signal is set. Otherwise, it'll be +1, which means that message is received. The very first message will be a 0 because that was how I created the queue in the first place, so I continue in that case. Otherwise, it should always be invoke call. I can now put L-param passed in as the marshal object, which I dynamic cast to that type of object. Call invoke, okay, which you saw. And then call this function to signal that the operation is completed. And all that does is set the event for the marshalling object, the original signal it began with. So that means that this wait will complete, whoever happens to be waiting on it, and they can go on to the next line, and I can go back to my wait. So again, going back to this, we post the message, right? We wait for that function call to complete, retrieve the return value, return value, put S1 gets called, but it gets called in a different thread. So we're getting in here. Okay, not in this first case. This is our A8. This is in hex. Maybe I better not. Let's not do hex. Because that's not listing in hex. Five, 6, 3, 6. Okay, that's our main thread. Alright, now I press the key. So here we are. Here's a call stack. Now, we can't, you see, it won't even let us go. Well, we can't go back here to where the actual call was issued. In terms of thread, in the other thread, in this thread, right, we are, here, okay? That's where we are. We're on put S2 in one thread, okay? Now a context switch occurred, and that put us in this thread, which put us into this print function, okay? So the call stack will not contain where the call was issued, because it was issued in a different thread context. With the same string and everything, the one we passed in. Now this marshalling thing is all related to that horrible COM stuff. So that's why I thought I might mention it. Now you're going to see these if you start to look at COM, you're going to see these things called apartments. Okay, like what's the apartment model, right? Now sometimes there's something called the single-threaded apartment, right? And if you search for the word marshal, okay, within an apartment, interface pointers can be passed without marshalling. So therefore, all objects in a single-threaded apartment thread communicate directly. So a COM call in a single-threaded apartment model is just a regular function call. However, calls into other processes must be made within the context of the owning process. So distributed COM, DCOM, switches threads for you automatically when you make a call on a proxy. And that's what we're doing. This is a proxy. Okay, this other thread is a proxy. It's the context within which the function call actually occurs. In this case, it doesn't matter. We can do it in either thread. But if it was in a different process, not only are we switching threads, we're switching address spaces. The data has to be copied through some global data structures and so on and so forth. And that, again, is called marshalling. Now, see, you're going to see words like co-marshal, inter-thread interface, in-stream. Okay. And this all they're talking about with this marshalling thing is what I just showed you. That's what it means. It means to line things up and have them occur in a particular context. Have everything occur in a particular marshaled context. Okay. Now that's what all these apartment models are about. Single-threaded, multi-threaded, choosing apartment model, in-proc server, right? In-process server might be single-threaded, might be multiple-threaded. There might be out-proc servers, okay? And all of these things require marshalling. And now you've seen how marshalling works, okay? All I've used here is a very simple example of a thread. We have a window, and we're going to marshal all of our calls to drawing into that window thread, right? And context. Remember, its memory context is different too. The HDC and everything allocated in its thread is only valid within the context of that window. That's why they call it a device context and not a device. It's a context associated with the drawing area and with all of the other GDI objects that exist in a window, or in a wind proc. A wind proc is actually one of these marshal things. It's one of these invokes, right? Essentially, when you look at a window running and you look at the call stack, eventually you see one of these things, okay, right? And that's where it switches context. Sometimes it switches context back to the same thread, but things like the stack has changed. It's not the same stack. The memory has been relocated or reallocated or something. And that's why, for instance, I believe I had that crash before where I bumped up the size of the stack, right, in the window prop. Whereas the stack size that I set for my program would have been for the main thread. It's context. And switching context, because the context got switched, and the thread and the stack grew to a large size, which was allowed. The marshaller has a bug in it, in which case it doesn't realize that the calls to check stack and everything have to be fixed up when the stack size is allowed to be bigger than the normal size. Anyway, that's marshalling in a nutshell, and that's what I'm going to do with the drawing. And now you understand marshalling. Now you know what an improc server has. Why these things are called servers. There's a server type thing going on here, right? This thread proc is a type of server. It serves function calls. You serve it function calls. So you ask it to do function calls, and it's a server that accepts requests to perform function calls in its context and return you. Wait till it's done and return the return value. Okay, see you, bye.